Hello, good afternoon. We resume our lecture on Six Sigma, and the session that we are starting right now is called Planning for DOE. And what we'll be doing is it continues from what we've been doing till now, and I'll begin with the slide which is there, which is a summary of what we've done so far. DOE is a systematic procedure design. It's a systematic and a rigorous approach to engineering problem solving. That is DOE. It applies principles, sound statistical principles and techniques at the data collection stage. That is something that DOE does. It assures the generation of valid, defensible, and supportable engineering conclusions. This is something that results if you conduct your experiments under the DOE framework. And all this is carried out under the constraints of minimum expenditure of engineering runs, time, and money, because the whole planning is quite efficient. Let's see how you go about planning for it. In fact, it turns out that the motivation for doing experiments, it can come from many different places. One of the key ones is, of course, development, product development, for example, or even process development. We start with design, we start with research, and we move toward design. And in going from this left end of the arrow there and moving to the right, we need to do a lot of experiments. That is like something that's one place we do a lot of work which is like this. Then of course we got to validate the process, and that validation, whether you've got the right design done, whether the process conditions are right, and so on and so forth. There again we can use experimental work. And then toward the end, when we do monitoring, that's when quality assurance is done. We got to make sure we monitor the right quantities. So this is like one large area, but many times the technique actually is experimental. So that's like something that is there whenever you're trying to realize a new product in particular. It's a way to gather data. Doing experiments is a way to gather data, but the problem is that what we learn depends very much on where we look. So if you're touching the elephant, depending on what part of the elephant you're touching, you'll end up learning just that kind of information. It's like also, how do we look? Do we have a blindfold on top of us, or can we see things? Can we touch things? Can we feel things? The scope of our view, what can we see and what we are not able to see? Resources utilized, time available, and material available. All these things basically, they control how much we learn and how we learn. When we do experiments, we are basically looking at a situation, a system, which has got signal factors, some control factors, and of course noise factors, and we're trying to measure the response there. Our goal really is one and single. We are trying to understand the process. This is primarily the goal of R&D. The goal of R&D basically is to try to sort of understand how does this process work. That's what we are trying to do there. We will see, specifically we'll try to see the effect of the various parameters as they are set at different levels, which are like called treatment levels. In fact, if you see the cost of experimentation, where does money go when I try to do experiments? Into resources, people, equipment, so on and so forth, time, material, and usable product that is not produced, that is not being produced. These are the places where we spend our money, and therefore what we have to do is we have to be most efficient. What are the different approaches by which experiments are done? Well, one way would be to build, test, and fix. Basically, you build something, you test it. If it does not work, you fix, and you come back and build it again, that kind of thing. This is like one way. The other way would be to change one factor. You have the full system in front of you. You keep twisting one factor at a time and see the response. If you did this, you would not be able to study interactions. The best way, of course, to generate empirical knowledge is to apply the DOE framework. If we did that, we'd be the farthest ahead. What happens if we try to build, test, and fix? This is really the tinkerer's approach. What does a tinkerer do? A tinkerer does not have any standard framework guiding him. He basically manipulates the different factors which are there. So if you give it to somebody, please see how this pen can be done something with. You would start tinkering with it. You'd probably manipulate the clip, manipulate this, manipulate that. You'd probably take the back end off. You'd probably take the tip off and so on. So you do basically manipulation. If I wanted to ask him, set the condition in such a way that it writes perfectly, a tinkerer will start playing with the different factors without any kind of systematic approach applied to it. In fact, that is the approach sometimes what we say, we force things to fit, then we paint it to match. That is the tinkerer's approach. Build, test, if it works fine, otherwise fix it again and build it again, rebuild it. It's impossible really to know whether your performance is optimum. That is like something that is not possible to figure out when it's just building, testing and fixing. Also, it's consistently slow. It's actually invariably this is a slow approach. Particularly when you see some of the advanced design of experiments approaches, you'd actually come to realize that we probably should not be spending even 1 rupee worth of material or time or resources by doing it this way, which is like build, test and fix. What about one factor at a time? That seems like quite scientific. A lot of people in chemistry and many in physics also, they run one factor at a time experiments, and we'll see what are the benefits. If indeed are there any benefits from this. The big problem with this is, which I put in red here, that if you do one factor at a time trials, you can miss interactions. Interactions are not there because you're manipulating one factor at a time. The moment you manipulate one factor at a time, you have no idea what would happen if 2 factors were changed together, or if 3 factors were changed together. What would happen? You would not know that if you're doing one factor at a time trials. What do you see as the result of a one factor at a time? Like for example, I've got a couple of situations here. I have really, the process is supposed to be affected by 2 variables, temperature and pressure. When I'm doing one factor at a time experiment, I fix one of the factors. So here in this case, I fixed pressure at 65 psi, and I manipulated temperature and looked at yield. So that was like response being observed when only one factor was changed, the other was fixed at this thing. So what do I see from this? I see, okay, when pressure is fixed at 65 psi, somewhere in between around 78 degrees Celsius, yield becomes maximum. Then I move to the next round of trials. In that case, I'll fix temperature at 78. 78 turned out to be the best point by the experiment done to the left. And then I find when I vary pressure at 130 psi, I get maximum. So now I'm praying and hoping that I've hit the optimum. The optimum is basically the peak here found. Use that in the next round of trials, and I found another peak there. And hopefully this is the best peak possible. Is that really the peak? In fact, have I really missed out something that is optimum? Let's take a look at the full process. Well, the full process has a response surface like this when I look at the full range of change of pressure possibilities and full range of temperature change possibilities. Our initial experiment, the one factor at a time experiment, it was stuck right there. In fact, it's stuck right there, and there's like way out. Yield can be much more. I never really got to that range there because I was stuck here by manipulating one factor at a time trials. I was stuck right there. So this is something I'll not be able to figure out if I continue to do one factor at a time experiment. I have no idea about the full response because I've not manipulated 2 factors together to see what that response is like. You change that to DOE. And what is the DOE approach? It's a statistical approach. It's a systematic approach. And it uses some special approaches. It uses factorial design, and in some cases it uses Taguchi design, and in some cases it uses what we call response surface design. These are schemes. These are experimental schemes that we use. We could use the full factorial design, or we could use the Taguchi design, or we could use what we call the response surface design. And these 3 approaches, they will give you different results, but these are all scientifically derived. These are all going to be scientifically derived. Let's take a look at the full factorial design. Right now, we are basically trying to plan a trial, plan an experiment. What does the full factorial design do? Full factorial experimental design do for us? It's the simplest design to create, but it's extremely inefficient because it ends up with sometimes a large number of trials. For example, if I had 8 factors, and if I had manipulated the 8 factors at 2 settings each, if I did that, I'd end up running 256 tests. That's way too many tests. And while you are manipulating these different 8 factors, it's possible that other factors also perhaps changed, and the conditions would differ from the first few experiments to the last few experiments. Those conditions, if they are different, then of course your whole experiment is fouled up. That is one of the problems with full factorial experiments, because really speaking, Many times the full factorial design requires you to run many experiments. That's like one of the shortcomings. But it's a pretty powerful method. It can let you find all the main effects, all the interaction effects, and in some cases it can also lead to that response surface. Those things can be done to some degree by using the full factorial design. What does it look like? Well, if I had three factors, if I had factor A, factor B and factor C to manipulate, and if each of those factors could be set at two levels, low and high, there is a way of combining the different factor settings. So I've got two levels of A, and I've got two levels of B, and I've got two levels of C. When I combine their setting to come up with the plan for the scheme for trial number 1, I'll set A at low level, B at low level, C at low level, and then observe the response. Run the process, observe the response. Then I change C from low to high and keep the settings for A at low and also B at low. Then I've got low, low, high. This is my trial number 2. Then I come to low, high, low. That's trial number 3. Then I've got low, high, high. That's trial number 4. Then of course I change the setting of A from low to high. I've got high, low, low, like the first one. Then I've got high, low, high. Then I've got high, high, low, and high, high, high. What are these settings? These are the different settings at which I can set factor A, I can set factor B, I can set factor C and run my trial. So here in fact I've ended up running 8 trials at these different conditions. This is kind of a combinatoric situation. I've combined the different settings possible for A with the different settings possible for B with the different settings possible for C. And each of these cases, each factor has 2 settings. So I've got 2 multiplied by 2 multiplied by 2, which is like 8 total trials. That's going to be my experimental plan. The fractional factorial design chops off part of the full factorial design. So it is not as powerful as the full factorial design. What does it give up? Sometimes it gives up interactions. Sometimes it gives up interactions. So some of the interaction effects might not be, in fact, you may not be able to determine the interaction effect if you're running what we call fractional factorial. These are part factorial. Here's an example. I have again 8 trials, but here what I've done is I've got factors A, B, C, D, E, F, G, 7 factors. If I'd run a full factorial experiment with 7 factors at 2 levels each, I would have had to run 128 trials. What have I chosen to do? I'm running only 8 trials and I'm running a special scheme. I'm running a special scheme of the experiment. And this special scheme is being run in such a way I can cover 2 settings of A, 2 settings of B and 2 settings of C, 2 settings of D, 2 settings of E, 2 settings of A, F and 2 settings of G. Having done this, I've got only 8 trials done. Of course, this scheme is not going to be as powerful. It's not going to be as powerful as the full factorial experiment. The result is this. I will be able to find the main effect, but I'll not be able to find any interaction effect. That's not something I'll be able to find with my partial factorial design. This is the example of a partial factorial design. Then of course I've got the third approach to conduct experiment, and the goal here is to try to generate the response surface. Here I've got 2 factors. I've got factor 1 and factor 2, and I run the experiment at many different points, and that helps me generate this surface there. This will be found by doing multiple regression. But in trying to produce the data, what I've done is I've set the level of A at multiple points. I've also set the level of B at multiple points, and at each of those points I've made an observation. At each of those intersections I've made an observation, I've collected the data, then I run my multiple regression model, multiple regression calculation, and I end up generating the surface. You can see the surface right there. This is actually something that is done when I'm trying to optimize, when I'm trying to just basically generate the response surface there. In fact, here is another example of a response surface, and it can let me manipulate 2 factors here, temperature and pressure. And of course, I've got something called duration, which could be the cooking time for this particular chemical process. Having done that, I'm able to now generate this model, and this model is actually a multiple regression model that I've generated with the help of this response surface design. So this is like the third design. So what are those three designs so far? I have full factorial design, I have a fractional factorial design, and I've got a response surface design. These are three different approaches to design my things. How do I go about illustrating design of experiments processes? I must, of course, the first thing I should do is determine the goals, like I said before. Define the measures of success. When am I going to say that I've succeeded in conducting the experiments? How am I going to check the feasibility of this thing? And then, of course, I've got to design the experiment, I've got to run the experiment, I've got to collect the data, I've got to do my data analysis, and then, of course, I've got to act on the results. Let's see how we end up doing that. Determining the goal. Determine the goals. And goals, generally speaking, certainly in the Six Sigma case, those are derived based on some business objective. Perhaps defect levels are high, perhaps yield is low or something like that, perhaps customer service is poor. Those we use as the response, and then we try to see what are the different factors that we can manipulate in trying to make sure we can do that. So the determining the goal is very important in starting your planning for conducting an experiment. Then define the measures of success. These are, of course, going to be how am I going to measure the output, how am I going to judge the output. That also will have to be spelled out. Then, of course, verify feasibility, and this actually says if I conduct my experiment in a noisy environment, will I be able to hear the signals? If I'm not going to be able to do that, then of course I have to make sure the noise is not that high. If noise is not going to be that high, then I've got to make sure when I finally apply the conclusions or the results that come out of an experiment to a practical situation, I do something to make sure the effect of noise again does not cloud my results. That is something that I'll have to be able to do. But in general, of course, something that turns out to be significant stays significant, because something that we call statistically significant is always measured with respect to the presence of background noise. And this is done by the ANOVA test. The ANOVA test makes sure that what you call significant really is significant. It's audible, is visible in the background of noise that is present there. And something, of course, we also have to do is, so we have to check out the feasibility of the thing. How many experiments can I run? What sort of precision do I want? And do I have the money to be able to run those trials? That is something that we'd like to be able to do. Then, of course, I got to make sure I specify the precision of the experiment. That is something that I've got to do. I've got to run the experiment. And that is a task that also needs to be randomized once in a while. This is something very important. Unless you randomize, there may be a factor like sunshine, for example. And if you run some of your trials in the morning when temperature is cool, then you run it at lunchtime when it's pretty warm, then you run it again in the evening when temperatures are cool again. These results may not be comparable because of the presence of this outside factor, which is the environmental factor. So this is something you also be able to watch out for. You should be able to watch out for. I collect and analyze data, and I always use statistical methods to analyze my data. Even if I draw some pictures once in a while, I draw some pictures. I really should be able to do this correctly. And of course, in the end, when I've conducted my experiments, I should be able to verify the response. This is something I should be able to do. And of course, the end is the proof is in the pudding. Therefore, once I've derived some inferences, derived some conclusions, I've got to make sure I run these trial tests. I've got to run these validation or verification tests to make sure what I inferred from this indeed pans out in the real world. It is something that we really see that. What are the considerations? Cost, of course, is a very big one. And then obtaining the material to be able to do this. Why are we trying to do all this? We basically want to understand the process. So when the real process runs, I do not have as many defects, as many rejections. What are the different approaches? I already showed you build to test, build, test and fix, one factor at a time trials and DOE trials. I'm going to expand on this a little bit, and also I'm going to give you some examples of factorial designs and the Taguchi way of designing experiments and the response service method. Other approaches were also there. For example, the full factorial method is there, like I told you earlier. The results of the full factorial trial, those are basically analyzed using ANOVA. Taguchi methods, on the other hand, lead to some very fairly simple, straightforward calculations. But the Taguchi approach to conducting experiments cannot really figure out many times interaction effects between 2 or 3 factors, because most of these they turn out to be factorial, partial factorial designs. So what is the summary of all this? I've got to determine the goals. I've got to define measures of success. I've got to verify feasibility. I've got to conduct the experiments, run the experiment, design and run the experiment, collect the data, look at the response, then come back and act on results. And in fact, in that situation, we should be able to basically verify what we've done. The conclusions that we reach, do they really confirm? If I identify some settings as optimum for A, optimum for B, optimum for C, when I combine the optimums, do I get the best results? That's a validation that we have to do. Now let's look at some applications. The first application I'm going to talk about is called application of Taguchi methods. This person, you see his picture there, he was an engineer and he was a pretty curious person. And he was very concerned about trying to impact the quality of products that are coming out of the Japanese factories. And he became involved in this game in the 60s. And that was about the time when he also came to India and he studied under Dr. C.R. Rao. C.R. Rao was his teacher, and C.R. Rao was a statistician. C.R. Rao right now is in Pennsylvania and is a professor there. C.R. Rao, when he was in the Indian Statistical Institute, he was Taguchi's guru. And Taguchi studied the design and conducted different experiments. One of the things that appealed to Taguchi was the simple design of partial factorial designs, and these did not require analysis of variance. And what Taguchi was able to see was, in many cases, we need not really run the full factorial design and would still be able to come up with pretty decent inferences. That is something that Taguchi was able to figure out. And let's see what he ended up doing. He ended up contributing something that is truly enormous. He was able to come up with a new philosophy for managing quality. And this we all call today the quality engineering philosophy. This is something Taguchi was able to contribute. He gave us a method which was simpler than the analysis of variance technique or the full factorial design. So those became fairly efficient design, and the analysis also was very simple. So these turned out to be pretty major contributions produced by Taguchi. Taguchi was able to articulate one other thing that was perhaps known to people, but they did not really put this down on paper and pencil. So really it was not knowledge that could be passed on to other people and so on. People had this feeling, but they never really knew how to exploit this. What is this issue? This shirt size, this shirt is perhaps a little too loose on me. If I had the choice, now this is probably because over aging, my neck has probably become slightly shorter. And this shirt is not very old, it's about 1.5 years, 2 years old, and it still is a fine shirt, nothing is wrong. But the fit is slightly off. If you look at the fit of this shirt, it's slightly off. As far as the customer is concerned, the customer is happiest when the product that he uses fits him exactly. So there is like a target dimension. There is a target dimension of my neck size, and that dimension could be 40 centimeters. If I were to choose a shirt today, I'd go to a tailor and I ask the tailor, please measure my neck size, and he'd give me the exact measurement. Then I'd walk up to the shelf or perhaps ask him, stitch me a shirt that's exactly 40.0 centimeters as far as neck size is concerned. Then of course you do the same thing with sleeve and so on and so forth. So the shirt that fits exactly is the one I'm going to be happiest with. The same thing goes for no matter what you do. Even if you look at a pen, for example, the thickness of the pen with which it writes. We have personal tastes, and there are certain tips that we do not like, certain tips are thick, we do not like them. So this is something that's got I've got a requirement, and that requirement specifies my target. So my target thickness is this. And if I've got a choice of many different pens, you give me a whole bunch of pens, I'll probably start using them I'll probably try to see which one comes close to my target and which one does not. This is something I'd like to figure out. Unless I do that, I would not be the happiest person. What Taguchi did was, he articulated these things by drawing this little picture here. And look at the picture there. The target is the place where the customer is happiest. If you move away, if you offer him a product whose dimension is away from the target or whose quality characteristic is away from the target, the customer is going to incur something that we call a loss. What is the conventional wisdom? The conventional wisdom is, well, if Professor Bagchi requires a shirt, his neck size is 40, but give him plus minus 1. Who fixes this tolerance? It is probably fixed by the tailor, or perhaps by the guys who merchandise the shirts, for example. They are the guys who fix this plus minus 1. Now, I'll not be as happy with a shirt size that is 39 or 41. I just would not be as happy. I need a shirt size that is exactly 40.0. And that is being right at this target there. If I'm at the target, I'm happiest. This tolerance, this sort of tolerance that is put down as low specification and high specification limits, this is like the old way to look at quality. What Taguchi said is, try to find out what the target is for a particular customer and offer him a product that is right exactly on target. That's when the customer's loss is going to be minimal. If this shirt does not fit me, suppose this were a new shirt, suppose somebody gifted me a shirt that was size 40, size 41 or 39, I certainly would not be able to use it. I'll have to take it to a tailor, ask him, please fit the shirt exact to my size. That's an additional cost and perhaps the fit won't be as good. So all those problems are there. The moment we start manipulating something that is off the target, we'd have to spend some extra money for it. And that's a loss to society, because this loss could be avoided altogether. Nobody gains from it. Therefore, basically the idea is, what Taguchi said, try to find out what the target is and keep it there. And this was coined as Taguchi's loss function. So you see that red curve there, that actually shows losses go up the moment you get away from the target. Either you give it some excess or you shrink something there. You'd end up with causing a loss to the customer, to the user. So Taguchi's views is keep your eye on the loss function there and try to deliver things which are right on target. And he even gave us an equation. And that equation basically tells us what would be the amount of loss if I deviated from the target. That is P performance minus T, which is the target. Square that, and there's a multiplier there. That basically gives you in quantitative terms what that amount of that loss is. This kind of it's a parabola, as you can actually see, and that is like the way your losses would increase if you went away from the if you went further and further away from the target there. Now this was verified by a couple of industrial situations. One of them was the production of televisions. Now there's a company, and this particular case is well documented. It came out in a newspaper in Japan, the Asahi paper reported on this. Let me tell you about this particular incident. There was a time when a lot of this is some years back, I'll say about 20-25 years back, when Sony TV produced the best TVs in the world pretty well, and the model was called Trinitron. This Trinitron TV was brought to US, and American consumers certainly found that these TVs, they performed much better. The color quality was good, sharpness was good, everything else was good. It was better than whatever they had on their shelves or in their homes there. So Sony's TVs, they started selling very, very well. And of course, Japan was exporting these Sony TVs from Japan into mainland USA. It was quite natural for Americans to begin to sort of feel that these guys, they're grabbing our market. They're even robbing people from their jobs. Those guys who work in American TV companies, they are probably going to be losing jobs because Sony TVs are basically flooding the market and so on. So there was a protest, and the result was that Sony decided that they would set up an assembly plant in San Diego. They would bring the parts and the assembly would be done in San Diego. So there, of course, American workforce was hired. A few supervisors came from Japan, they did some training. After that, they went away. It was given completely to Sony USA, which was an American company. And of course, production started, and these TVs coming out of San Diego, California, they then got to the shelves of these different stores. It turned out after about 6 months or perhaps a year, people started complaining about Sony TVs. And this was very strange because Sony had had the reputation of producing the best TVs that you could find anywhere. Suddenly they started getting complaints. And they are pretty smart people. What the Japanese troubleshooters tried to do was they tried to look at the model, and they looked at the back of it. There was a batch number there. There was a location specified where that particular TV was assembled, where did the parts come from, and so on. And they found many of these actually came from San Diego. These came from San Diego, and these were actually the ones that were causing the maximum amount of problems. And this was a crazy situation, because what happened here was that the TVs that was otherwise supposed to be good, they suddenly started, because the parts were good, these started to show problems. And this was a really crazy situation. What they did was they looked at the assembly process. And what they found was that the assembler who was an American and he was doing this assembly on a production line, he had the spec in front of him. And the specification was given just like this. There was a lower specification limit and an upper specification limit. As long as the parts came together, it was all right. As long as they meet the specification, it was all right. And the parts were put together and the full TV was assembled. Each of those parts could be anywhere in this specification range. Each of those parts could be anywhere in this specification range. And of course, that is what the full TV turned out to be. The full TV turned out to be an assembly of parts that had this sort of slack fitting. And this specifically impacted the color quality and the sharpness of the TV. And naturally, these TVs, they were assembled with this philosophy. These TVs would not perform as well as those TVs, as nicely as those TVs that were made in Japan and assembled all the time to hit exactly the target. So as far as customer satisfaction was concerned, it turned out customer satisfaction was maximum when TVs basically were assembled with the philosophy of being put together with the target in mind, and customer satisfaction was not as high when they were basically put together with this philosophy of just meeting specifications. This is something where we got the graphic feedback that it is best to produce parts and products that meet the target. So do not go to try to produce things that come within specification. This is something Taguchi said. He said, do not produce things that just meet specification. Try to find the target and try to hit the target every time. If you do that, customer satisfaction is going to be maximum and your market share is going to grow. This is one message that came from Taguchi. Taguchi came up with another remarkable insight, and that is called robust design. And let me give you an idea what this thing is. Notice here what we have is we have a product. For example, if you look at a chocolate bar, for example, the chocolate bar basically is designed using the best recipe that is there, and you end up with the chocolate bar being put together with some nuts, some cocoa, some milk, some sugar, some butter, and so on and so forth, and the bar is cast. Then the bar, of course, when it gets stable, it's packaged and so on and so forth, it is shown. So no matter which chocolate bar you look at, the manufacturing process is exactly the same. Now these obviously are very popular products. This is something everybody likes. Especially kids, they just love. You give them one, they are generally not happy, they would like to take another one. But who are the people who are unhappy with chocolate bars? You can probably guess, these are mothers. Because what happens? When a kid buys a chocolate bar, he'll take the first one, he'll probably start munching. If he gets another one, he's going to stick that in his pocket. So the chocolate bar gets in his pocket. This one, by the time the kid ends up eating half of it, the other half has already melted because of body temperature. A chocolate bar is something that melts very easily. If I store the chocolate bar, if I store these chocolate bars in a place where temperature is 20 degrees Celsius, there'll be no problem at all. But look at the temperature outside. Today outside, this Kharagpur, this building, if you go outside, temperature outside is 36 degrees. And then of course, I had some fear. When I took them out of my drawer and I tried to bring them to the studio there, I had some fear that maybe the bars are going to melt. So I had to wrap something around it to make sure it's still got here in a solid piece. Now, this is exactly what the complaint is from mothers. Mothers say that the plasticity of these chocolate bars is too sensitive to ambient temperature. And let me show that by drawing a little picture here. I'll put down ambient temperature here. So temperature is going to be, T is here, temperature. This is low temperature. So this would be like 10 Celsius. This I could put at 40 Celsius. And 20 Celsius somewhere around here is 20. This is ambient temperature. Now the other condition that is also there is plasticity, that is the response. So I'll just put down plasticity. Plasticity, that is this. That is the ease with which it can melt. So around here is pretty solid, and around here is going to be almost liquid, semi-liquid. Semi-liquid. That is the status of plasticity for chocolate. Now, what happens to a normal bar, the one that is like this, Cadbury Dairy Milk? If I take this bar, if I subject to some experiment, and if I look at the condition of the chocolate bar, gradually it's going to melt, gradually it's going to bend and so on. And what is going to happen is, it's going to go like this. Plasticity is going to rise. It's going to go like this. It's going to become almost fluid at 50 degrees Celsius. It's going to be almost solid, pretty difficult to bite around 10 degrees Celsius or even below that. That's not something that's going to be very popular with mothers, because mothers have to wash. Mothers basically have to clean the shirts and so on. So if I had one of these bars in my pocket, and I forgot that the bar was there, by the time I reach my office, from the studio when I reach my office, this is going to be a molten blob. So it's not going to be something that's going to be very popular. Now suppose there was a company that actually was very perceptive of this problem that is faced by consumers. What about kids? Well, kids like them when they are semi-solid, but kids obviously don't like them when they become all gooey. What would be a good way to go from there? Well, redesign the chocolate bar, redesign this guy, redesign this guy. How would I redesign? Well, change the recipe. There are multiple factors that I can manipulate, and if I do that using DOE, I can come up with a bar that would be like this. That is nearly stable. This is a robust bar. This is a robust bar, and certainly this is not a robust bar. How do I convert a design that is here to this one? How do I do that? That will be done using DOE, design of experiments. This is done by doing DOE. If I did DOE, I'd be able to take a product that is not so good, I'd be able to convert it to this sort of situation. This is something that would like to be able to do. So this is like one great application. This is like one really, really good application of robust design and the manipulation of the different design variables using the DOE framework. This is a great way to come up with better quality products. In fact, then of course the chocolate bars, we have to make sure that the hardness is not too hard. How do I do that? I have to find the target. Remember the target with the TVs? I have to find the same sort of hardness, the target hardness for kids. For that, what I could do is I could produce chocolate bars at different hardness. I could distribute them free of charge in a class. I could just see who is struggling and who is not struggling, and what is the strength at which most kids seem to be manipulating the chocolate bars pretty easily. I've got a good design now. I've got the target located, and also I've made it robust by applying DOE to the original design which was there. That was not going to be such a good. This is like a great contribution that Taguchi made. Robust design. How did Taguchi go about doing this? Let me just give you an example. Let me give you an example of what he had a different kind of insight. Now you recognize that this matrix here is a lot like what we've done before. I have three factors B, D, and O, and I've got two settings for each of those factors. And the result is I've got this 2 cube, which is like 8 trial experiments. And these are, of course, the responses that I observed. Notice these responses are the average responses. These responses are the average responses. What Taguchi said was, of course, the average response would depend on the setting of the factors. But so does the variance of responses. And what is the variance caused by? It is caused by noise factors. Because I could have, for example, I could have here, the response is 75. But if I made multiple measurements, if I made replications of this particular setting, I would end up with values that would be probably 75.3, 75.2, 74.9, 746, and so on. So the average would be 75. There would be a variance around it. There would be variance around this, and so on. If there's a lot of variance like this, my final product in the final process is not going to be a robust kind of a process. And for this, what I have to do is I have to really change what I'm looking at. I've been looking at average response before. What Taguchi is telling us is, do not just look at the average response. Take a good look at variability, which is like S square, which is right at the bottom of your screen there. Also take a look at that S square, which is the variance that is caused by noise. So when I've got this experiment running there, take a look at what is the impact of the different factor settings on S square there. So I measured S square all around. So not only I'm trying to look at the effect of our variation on look at the effect of the different factors on average response, but also I'll be looking at the variance of that response. This is the idea that was exploited when Taguchi came up with a scheme to develop robust design. What he did was, for that he included noise factors also in his experiments. In the traditional experiments, only control factors were used. What Taguchi did was, he said, my goal is going to be something different. I do not just want the average response to be optimized. I also want to make sure that my response is robust. And for that, I need to bring in temperature. In the case of what we manipulated, in the case of our robust design, which was using remember this picture that I had there? This picture? Here, the design variables would be all the things that go into the chocolate bar. And this is my ambient factor. So what Taguchi said is, when you're trying to produce a robust design, do not only manipulate these design factors, but also manipulate this and look at the total response. Look at the total response, which is now the composite, and it is indeed the interaction of the design variables, effect of the design variables, and that of the ambient condition or the noise condition. This is exactly what he did when you look at my slide there. He brings in the new scheme of things, when he's trying to get robust designs built, he's using noise factors also alongside everything else that he's trying to manipulate, which would be the design factors. The idea is to try to come up with performance that has got smallest variance when subjected to noise. In the case of chocolate bar, the response was plasticity. And I manipulated noise when I was changing my design variables, when I was changing the recipe, butter, cocoa, sugar, blah, blah, those things. When I was changing them, I also changed temperature. And I wanted to see what sort of setting of these different design variables would make plasticity most resistant to change in temperature. That would really result with a robust chocolate bar, basically, robust design chocolate bar. That's exactly what is done. Of course, when you're manipulating simultaneously many different variables, the only way to do that is using a DOE setup. And that we can, of course, see DOE is a key element in the Taguchi method. And if you look at the plans which are used, Taguchi's plans, they look a lot like the full factorial design. But something I've got to remind you of, Taguchi is not trying to use ANOVA. Taguchi does not really try to explicitly monitor or measure interaction between factor effects. Taguchi does not try to do that. He does try to figure out the interaction between noise factors and design factors. That is one thing that he tries to do. And in that approach, he has stayed with just partial factorial design. and he calls them orthogonal arrays. This is a special name given by Taguchi to certain classes of these fractional factorial design. And some examples are there. Here's an example of a Taguchi array. These, of course, these have become commonly known now as Taguchi array. They've existed before. We've had them before. Not that these designs are different, not that these designs are new. These have been created by statisticians way before Taguchi came around. But Taguchi used them in a very special way, and he popularized this thing. So that's why these arrays or these design plans, they have become known as Taguchi arrays. Taguchi's L8 arrays or L12 arrays or L16 arrays. Basically here, if you look at columns, I have 7 factors that I can manipulate. So certainly for a chocolate bar, again if you go back to chocolate bar, there are many factors there, probably 7 or 8 different factors. So if I had to run experiments using a chocolate bar, for building chocolate bars of different types, I'll have to manipulate these 7 or 8 variables together. In trying to manipulate all these different variables, I can't really use the full factorial plan because it's going to be too large. It's going to be an overkill. Instead, I use fractional factorial design, like the design that is shown here. This design can handle up to 7 factors, and there are other schemes that can handle several more factors. This is exactly what is used by Taguchi in trying to do this. Now, how does Taguchi bring in noise into all this? Look at the matrix inside. This matrix is also now a experimental design plan. It's a DOE plan. So I have here basically 3 design variables. These design factors are I1, I2 and I3. I've got I1, I2 and I3. And I manipulate these at 2 levels each. The result is 2 times 2 times 2 again. I've got 8 possible variations of factor settings or treatments as far as design factors are concerned. There are 3 design factors and each can be set at 2 levels. Because each can be set at 2 levels, I can now construct a 2 by 2 by 2 or a 8 row matrix. That is exactly what I show in the inner box. Look at the corners. Look at the corners. The corners basically seem to have another matrix imposed on it. These corner matrices, these are constructed by using basically what we call noise factors. In the case of our chocolate design, the noise factor was ambient condition. That is all. That was the only one noise factor that seemed to be basically affecting the quality of these chocolate bars. So basically, in those cases, I could just manipulate these this ambient factor at different settings. I could do that, and I could make this product robust. When it came to doing the design using 2 factors, and I've got 2 factors there. These 2 environmental factors are E1 and E2. The way Taguchi combined, he said, bring in not only your design factors to do a robust design experiment, robust design set of experiments, but you've got to also bring in these environmental factors or these what we call noise factors. For that, what you also have to do is you have to select the settings for these noise factors. Like for the chocolate bar, we used temperature variation. We had temperature variation from 10, then we went to 20, then we went to 30, then we went to 40, and looked at the trace, look at the effect of it. That we did with different recipes. So we found the recipe that did not really change as much as temperature was changed. As temperature was changed, we found plasticity stayed more or less the same. That was the recipe, that was the robust recipe. To find that, what I have to do in the case of the matrix design is I construct 8, call it prototypes. I construct 8 prototypes. I've got prototype 1, prototype 2, prototype 3, prototype 4. These are 4 prototypes built by changing I1 and I2. Then I change I3 also. And I produce 4 more prototypes. In all, I've got 8 prototypes. What is my objective? I want to find that prototype which is least affected by the shaking done by noise. And that shaking will be done identically to each of these prototypes. That is being done by these small matrices. Look at these small matrices. These are now going to be shaking those prototypes. So here, this prototype will be shaken over 4 settings of noise. This one also will be shaken by 4 settings of noise. Just to kind of give you an example, if you look at me, I've got a few objects on my table here, and I've got this computer screen also on my thing there, and I'm also sitting on a chair. Now, there is a big difference between a chair and a table when it comes to placing the screen. Obviously, we do not want the screen to be placed on a piece of furniture that is wobbly, because that would create a lot of vibration on the screen there, and perhaps it would be difficult to see the image that would be there. Rather, would like to take a robust sort of thing. Now, how do I find out? How do I find out which furniture? Suppose I got some new furniture. I got some Italian tables, I got some cane-made furniture and so on and so forth. And I had to select a table that was going to be a robust table. That was going to be a table that would be okay for placing my screen here, my computer screen here. What would I do? I would go to that furniture, whatever furniture it was, I'd try to shake it. I'd try to shake the table. I'd try to shake the table. I'd try to shake the table. And I'd find the table that is moved the least when I try to shake them with my hand. This is exactly what I'm doing when I'm shaking these four different prototypes. I'm manipulating these 4 different prototypes and I'm trying to shake them. When I do that, I've tested the 8 different designs here under identical noisy condition. And I'll look for the design that is most stable. This is the robust design. That was the insight that Taguchi developed. I've given you here an example. I've got the same design factors, I1, I2, and I3. I've got a matrix here, which is like the box that we saw there, the inner box. And the outer box is this upper box here. And for each of those cases, I've basically run my trials. And from this, I work out my output mean, which is the average response, and also the output standard deviation. This is the measure of that shakiness. This is the measure of that vibration. This is the measure of the kind of response that we see for the chocolate bar. This is going to be a wide variation. So S square is going to be large here. S square is going to be quite small here. S square across here is quite small. S square across here. S square is a sample standard deviation. Sample variance. Sample variance is high here. Sample variance is low here. We are seeking, when I'm trying to design a robust chocolate bar, I'm trying to seek that design which is smallest amount of S square. And this is exactly what we'll be looking for when we look at our matrix here. And we'll try to find the variation, we'll try and find the setting of it, which gives me the smallest variation. So as far as strength is concerned, this is the setting 1, 1, minus 1, settings for I1, I2, and I3. This is going to give me the strongest signal, that is the maximum amount of output means. But as far as robustness is concerned, it's going to be this setting there, minus 1, 1, 1. So this is going to be low, high, high. If those are the settings used for I1, I2, and I3, you can go back and kind of locate that thing there. I have low, high, high. So let's see that. Low for I1, high for I3, and high for this. So it is this point here. This is the point that is most robust. That's the one that has given me a standard deviation of 8.1. There are other methods also. Taguchi also suggested that we use something called signal to noise ratio. Taguchi was actually an electrical engineer, so he played a lot with signals and noise and that kind of thing. So being in electronics and electrical engineering, he kind of thought this would be a good way to check robustness. Of course, many other people, they have felt that probably signal to noise ratio is not the way we can get the best design. There are many other methods that have come along. But something you've got to remember, even if these methods are there, the philosophy stays the same. You may not, for your own application, you may not use signal to noise ratio. But still, the idea of robustness is something that you should really capitalize on. This is something that's going to give us really, really good performance. And I could do the same plots here. I plotted my torque. I plotted some standard deviation there, and also plotted the signal to noise ratio. And Taguchi says to get a robust design, try to maximize signal to noise ratio. And this is exactly what we've done, and we've got the optimum setting for this. This is something that we could do. Now the classical design looks like the same, but Taguchi's columns are somewhat different from the way our factors are assigned in the classical case. We sometimes saturate the design by applying many more factors. This is something Taguchi did to try to make sure that he got large number of factors covered. In fact, there are many plans that Taguchi has suggested, and those are listed under different types of L. These many lines are there in the matrix. So he's got L4 design or L8 design or L16 design and so on and so forth. These are different designs that basically have different approaches, and they give you this thing. This was one major application of DOE. Of course, you could use DOE to try to optimize, to try to come up with the best settings, but here you're getting robustness. This is something that we did not do when we were working before. I'll continue with another application, which would be the response surface method that will be done in the next class. Thank you very much.